Well, I guess it's this activity under buffers. So be sure to do these assignments as well. Did you see, can you see my,
Yeah, of course, I will finish them.
okay, good. So yeah, let's just go over buffers again. And let's just do a little review. So are you not able to access these lessons as well?
No, only the lessons that I've finished the activity on. So like the first three
I see.
lessons. The other lessons just give me the normal, you have seen more than one page of this lesson already, since we have already finished the lessons.
All right, so let's start buffers, okay? Let's review this a little bit, okay? All right.
On buffers. So let's get started. So all pH curves involving or titration curves involving a weak acid or a weak base have at least one region where a buffering action occurs. And a buffering region is where the pH changes very little, despite the addition of a considerable amount of acid or base. So it's a region where you're adding more acid or more base at quite a high level, but the pH is changing very little. So it's like buffering. The curves in these relatively constant pH regions are almost nearly horizontal. So that middle region of those titration pH curves.
Can you still see the video, Hala? The buffer, my screen,
Yes, I can still see your screen.
can you still see my screen? Okay, perfect.
At a volume of titrant that is basically 1/2 the volume at the equivalence point. So you're adding more and more of the acid or base, but the pH is not changing. And the solution near these points has a special significance, which is called that buffer solution, or simply just a buffer. So it's a mixture of conjugate acid-base pair that maintains a nearly constant pH when diluted or when strong acid or base is added. And it's an equal mixture of a weak acid and its conjugate base. So they resist change in pH when a moderate amount of acid or base is added. A weak acid and a salt of its conjugate base will be a buffer, or you can have this weak base and then a salt of its conjugate acid together.
Okay, Hala, so I'm gonna go over, I'm gonna start with weak acid
or a weak base.
now, like, because I feel like we need to finish listening to this first, and then we can go over the bases.
Hello everyone, welcome to Unit 1, Lesson 6. We're talking about weak acids and bases.
I don't think I remember. Okay, so this I've done.
Hello everyone and welcome to Unit 1, Lesson 5. Today we're talking about acid-base equilibrium, so let's get started.
We've done this one, but just this one we have not seen
Hello
together.
everyone, welcome to Unit 1, Lesson 6.
So I'm going to play this instead.
About weak acids and bases today, so let's get started.
Hella, are you there?
Yes, I am.
You're perfect. So you see this chart here, it's basically a pH scale, right? So the topic is acids and bases. So obviously your stomach is quite acidic with a pH of 2, and household bleach is basic. Basically, it doesn't really have much acid in it. So it's a very high base. And then you have your tomatoes and urine, and then water, of course, is supposed to be a pH of 7, which is neutral, right? Because we don't want to be drinking, we drink water to hydrate ourselves and nourish our bodies. So obviously we don't want to be drinking something that's gonna throw our bodies off of the pH, uh, like we don't want to be drinking, let's say, gastric juices or something, something like that. But yeah, the human urine is pH of 5. Pure water is 7 pH. Human blood is pH of 7.4. And then hand soap is pH of 10. And then bleach is pH of 12.
So curriculum expectations, similar to the previous lessons, we are using appropriate terminology, solving problems related to equilibrium, identifying common equilibrium constants. For learning goal and success criteria, students will identify common equilibrium constants and explain the relationships between Ka and Kb by calculating percent ionization of weak acids and weak bases and writing the expressions for Ka, Kb, and Kw. So many common substances are weak acids or weak bases, meaning that when they're dissolved in water, they form solutions that contain unreacted molecules in dynamic equilibrium with the ions formed by the reaction. And we can describe the equilibrium of weak acids and bases both qualitatively and quantitatively. And like all equilibrium, the reaction of weak acids and bases with water can be shifted to the left or to the right by the additional removal of reactants or products. So a weak acid, by definition, is an acid that partially ionizes in solution, but exists primarily in the form of molecules. So it's a weak electrolyte, does not ionize completely in water to form hydrogen ions. Most common acids are weak. And weak bases is a base that has a weak attraction for protons. Right, so these solutions are not as basic as, for example, ionic hydroxide solutions. So they're weak bases. Some molecular and ionic compounds other than hydroxides also dissolve in water, but not completely. And many naturally occurring acids are carboxylic acids, which are weak acids. And other common inorganic weak acids include hydrofluoric acid, which is HF, carbonic acid, which is in soft drinks, H2CO3, hydrosulfuric acid, H2S, and boric acid, which is like in Iowa solutions, H3BO3. And then solutions such as ammonia and sodium phosphate are considered to be weak bases. So for a general weak acid ionization reaction, you have HA yielding H plus plus A minus. That's our general equation, where HA represents a weak acid. So therefore, we can put together our Kc, or our acid dissociation constant, Ka, to be the concentration of HA times the concentration of A minus over the concentration of your weak acid of HA. Another way we can express the acid dissociation constant is with the formula HA plus H2O yields H3O plus A minus, and we get our Ka to be H3O plus, the concentration, times the concentration of A minus over the concentration of HA. Right, all concentrations are those at equilibrium. And note that the smaller the value of Ka, the weaker the acid is. So measuring the strengths of different weak acids according to their Ka. Stronger acids have a large Ka, weaker acids have a small Ka. So here's some examples: nitrous acid, acetic acid, and hydrocyanic acid. And their associated Ka values. So the stronger acids have the larger Ka, and the weaker acids at the bottom have the smaller Ka. So calculating Ka from your pH. Here's an example, and you can give this a try if you feel confident enough to before we get into the solution. A student prepared a 0.1 molar solution of formic acid and measured its pH to be 2.38 at 25 degrees. Calculate the Ka. So your plan, you're going to convert pH to a concentration of H3O plus, create your ice table to determine the equilibrium concentrations, and then solve using your variables for Ka. For solution, step 1, convert pH to our concentration of H3O plus or H plus. So our pH, we know our formula is equal to negative log of concentration of H plus, and that's going to be equal to 2.38. We were given our pH. So our log of H plus is negative 2.38, and we put that to the base power of 10 to do the opposite of the log function. So we get the concentration of H plus to be 4.2 times 10 to the negative 3. We create an ice chart to determine the equilibrium concentrations. We're starting out with 0.1 concentration of our formic acid and 0 concentration of our products. The change is a minus x, or minus 4.2 times 10 to the negative 3. And then this is a 1-to-1-to-1 ratio. For the products, it's plus 4.2 times 10 to the negative 3. So for our equilibrium of our formic acid is 0.1 minus 4.2 times 10 to the negative 3. And we can solve for Ka using our equation, which is going to be 4.2 times 10 to the negative 3 times 4.2 times 10 to the negative 3, because the concentration of each H plus and HCOO minus are the same. It's a 1-to-1 ratio. Divided by the concentration, your final concentration of your formic acid, 0.10, and we get 1.8 times 10 to the negative 4. We can also define percent ionization of weak acid. So if you were to measure the pH of two solutions of equal concentration, one a weak acid and one a strong base, you would find that the pH of the weak acid is closer to 7. So measurements of pH indicate that most weak acids ionize less than 50%. Right, so we can calculate percent ionization as P equals the concentration of the acid that's ionized over the concentration of the acid solute, or the original concentration, times 100. Also written as, when we have that general weak acid ionization reaction, P is going to be equal to the concentration of H plus over the concentration of HA times 100. So for example, if a 0.035 molar solution of HNO2 contains 3.7 times 10 to the negative 3 moles of H plus, what is your percent ionization? What is the concentration of H plus, which was the 3.7 times 10 to the negative 3 over your initial concentration of your acid, 0.035 times 100, and you get 11% ionization. We can also use our Ka to calculate pH. So knowing the value of Ka plus your initial concentrations, we can calculate the concentration of H plus in a solution of weak acid using an ice chart. So let's go through an example of that. Let's calculate the pH of a 0.3 molar solution of acetic acid, which is the weak acid responsible for the odor and acidity of vinegar, and the Ka of it is 1.8 times 10 to the negative 5. So step 1, we write our ionization equilibrium. CH3COOH is going to dissociate into H plus and then CH3COO minus ions. We can write our equilibrium constant expression, which is the concentration of both of our products over the concentration of the reactant. We know that's going to be equal to 1.8 times 10 to the negative 5. So let's continue on the next slide. So step 3, put together our ice chart, our initial change in equilibrium values using X to represent our change. Our initial concentration of our acetic acid is 0.3. The change is, well, minus X. It's 1 to 1 to 1. So 0.30 minus X. And our equilibrium concentrations of our products is just plus X. So we put in our values using our variables. And we get our K to be 1.8 times 10 to the negative 5. Let's continue solving this, or well, we're given that 1.8 times 10 to the negative 5 already. So let's continue on the next slide, simplifying this expression. So we have our formula. We get x squared plus 1.8 times 10 to the negative 5x minus 5.4 times 10 to the negative 6 equals 0. We can use our quadratic formula, and when you use that, you get two possible options for x. The negative one is the one that we're going to omit. It's not possible to have a negative concentration. So therefore, the concentration of H plus is 2.3 times 10 to the negative 3. And now that we have that, we can use our logarithmic formula to find the pH, right? So we plug that in for log H plus, for negative log H plus, and we get a pH of 2.64. Just another example of calculating percent ionization. The pH of a 0.1 mole per liter methanoic acid solution is 2.38. Calculate percent ionization of methanoic acid. First, you write your ionization equation, list your known values underneath it. It's a good method to get yourself organized. We have our concentration of methanoic acid be 0.1 and the pH to be 2.38. We can then calculate the concentration of H plus using the solution's pH and our inverse of our logarithmic equation, which is base 10 to the power of negative pH. And we get 4.2 times 10 to the negative 3. And then we can use our percent ionization equation to calculate your PI. That is the concentration of H plus is P time over 100 times HA, but we are going to rearrange that for P. So that's our formula that we were given on the previous slide, the concentration of H plus over the concentration of HA times 100. When we plug those values in, we get a percent ionization of 4.2. Moving on to weak bases. So just like weak acids, weak bases like ammonia, for example, form dynamic equilibrium in aqueous solutions. So we have our general equation given here as B, so your weak base plus H2O yields are HB plus and OH minus. B is your weak base. It attracts a proton from water, creating HB plus, which is that conjugate acid, and then your OH minus, which is your hydroxide ions. Instead of Ka, we have our constant of Kb. This is called our base dissociation constant or a base ionization constant. It always refers to the equilibrium in which a base reacts with water to form its corresponding acid and the hydroxide ion. So we have our base plus our acid yields our conjugate acid plus our conjugate base. And we get our base ionization constant to be the concentration of HB, your conjugate acid, times the concentration of your hydroxide ion, your conjugate base, all over the concentration of your base, your initial base. And here's a useful table listing some common weak bases. Notice many, or a couple of them there contain nitrogen atoms. So here's our Kb values of selected weak bases at 25 degrees. Like ammonia, pyridine, your carbonate ion, your hypochlorite ion, and so on and so forth. It gives the equilibrium reaction and your Kb for each of those. So we can use Kb to calculate the concentration of our hydroxide ions. So here's an example. Calculate the concentration of OH minus in a 0.15 molar solution of NH3, and the Kb at 25 degrees is 1.8 times 10 to the negative 5. So we're going to use those same steps used in solving ionization of weak acids as we will for weak bases here. You write your ionization equation, you set up your corresponding equilibrium constant expression, and go your ice table and solve for X. And once you have your known concentration of OH minus, you can calculate percent ionization using the formula. You can also calculate pH and pOH. So here's a solution. We set up our ice table with our initial concentrations, our change using X and our mole ratios, and then our equilibrium concentrations. We then put together our Kb expression, which is the concentration of those products over the concentration of the weak acid. Fill those in for X. Solve that or simplify that using our quadratic expression, taking the positive value of those, and therefore X is equal to the concentration of our OH ion, which is equal to 1.6 times 10 to the negative 3. We can now use that value to then use our other formulas to calculate pH, pOH, and percent ionization, right? Remember, using our logarithmic formulas and our P formula. Now we can talk about the relationship between Ka and Kb. And the next couple of slides sort of go through the mathematical reasoning for how we deduce this relationship, and then we'll get to what the relationship is. So recall that NH3 and NH4 plus are a conjugate acid base pair. We have our two formulas here, one for an acid or one for NH4 plus associated into NH3 and H plus, and then NH3 plus H2O dissociating into NH4 plus OH minus. We write out our expressions, our K expressions for number 1 and number 2, equation 1 and 2, as follows. And if we were to add the equations together, we're left with only the auto-ionization of water, right? If you add them together and cancel out what's there, you just are left with H2O yields H plus plus OH minus. So we can say that Ka times Kb is equal to our Kw. When we add two equations together to produce a third, that K3 is equivalent to our K1 times K2. So look at another example. Acetic acid is a common weak acid that in the aqueous solution forms a dynamic equilibrium with H plus and its conjugate base, which is the acetate ion, CH3COO minus. The chemical equation for this reaction is given here, and its associated equilibrium law expression is given as well, is your Ka. As a base, the acetate ion, CH3COO minus, may also react with water, according to this following, the second following equation given. And the base equilibrium law expression associated with that reaction is given here as Kb. But is there a relationship between the Ka of acetic acid and the Kb of its conjugate base, the acetate ion? So notice that most of the terms in the two equilibrium constant expressions are similar. If we add the two equations together and cancel the common entities out that appear as reactants and products, again, we're just left with the auto-ionization of water. So it can be shown that when reactions are summed up like this, the resulting equilibrium constant, in this case Kw, is equivalent to the product of the equilibrium constants of the constituent reactants. So therefore, we get Kw is equal to Ka times Kb. So when we quantify a relationship between Kw, Ka, and Kb, we get that Kw equals Ka times Kb for the concentration of H3O plus times the concentration of OH minus, which is equal to 1 times 10 to the negative 14. And we get two other equations as well. So for acids and bases whose chemical formulas differ by only a hydrogen, so we're talking about conjugate acid-base pairs, Ka is equal to Kw over Kb, and Kb is equal to Kw over Ka. Right? And then Kw is equal to Ka times Kb. So those are those three important equations to remember here, which allow us to convert Ka into Kb and given our value of Kw. So we can, that's the relationship between these three values, and we can do the equations if we're given some to find a different value. Let's look at an example of calculating Kb or Ka. What is the value of the base ionization constant Kb or the acetate ion at standard atmospheric temperature and pressure? So in order to calculate the Kb for this base, we must be given the Ka of its conjugate acid. We know that Kw is 1.0 times 10 to the negative 14. And the Ka of our acetic acid may be obtained from one of those reference tables that we talked about that listed all the Kas. So in this case, the Ka, and in the tester, you'll be given what the Ka is. In this case, the Ka is 1.8 times 10 to the negative 5, which was taken from your chart, from the appendix. And we can write our mathematical expression, Ka times Kb equals Kw, rearrange for Kb, which is Kw over Ka, plug in our two values, and we get a Kb, or the base ionization constant for the acetate ion, to be 5.6 times 10 to the negative 10 moles per liter. Looking at another example here, a very similar thing. You can go through this one a little bit on your own. The Kb for hydrazine is 1.7 times 10 to the negative 6. What's the Ka of its conjugate acid? We know Kw is always 1.0 times 10 to the negative 14. In this case, our Kb is given. It's the 1.7 times 10 to the negative 6. So we rearrange our formula to find Ka. You'll do showing some of the ionization constants have different conjugate pairs, right? So you could refer to this table when you're looking for a Ka or a Kb value. So the larger the value of Ka, the smaller the value of Kb. Because in general, the weaker the acid, the stronger its conjugate base. An analysis of various Ka values for acids of different strengths, and then the strengths of their respective conjugate bases, leads us to these important generalization or sort of rules. Number one, the conjugate base of a strong acid is a very weak base. The conjugate base of a weak acid is a weak base. The conjugate base of a very weak acid is a strong base, and so on and so forth. You can read through the rest. The special case we're going to talk about is polyprotic acids. So some acids, like sulfuric acid and boric acid, possess more than one ionizable proton. So because of this, they are called polyprotic acids. Specifically, sulfuric acid is a diprotic acid because it can donate 2 H plus ions per molecule. Boric acid is a triprotic acid because it can produce 3 H plus ions. So polyprotic acids do not donate all of their protons at the same time when they react, and they always ionize in a stepwise fashion, releasing 1 proton at a time. So looking at an example here, the following reaction sequence illustrates the ionization of arsenic acid. So note that each ionization reaction possesses its own acid ionization constant, designated Ka1 for the first ionization reaction, Ka2 for the second reaction. So going through this, notice that the value of Ka1 is much greater than the value of Ka2. This is true for most polyprotic acids. So the acid involved in each step of the multi-step ionization gets progressively weaker. See this as well in this table of acid ionization constants for polyprotic acids. So in general, the Ka1 is going to be greater than the Ka2, which will be greater than the Ka3, and so on for however many ionizations there are. One final example of just finding your Ka when you're given the concentration and the pH. So calculate the Ka of 0.05 moles per liter solution of nicotinic acid, the pH of 3.08. So we're given our pH of 3.08. We can find our concentration of H plus by doing our base 10 to the power of negative pH formula. And we get the concentration of H plus to be 8.3 times 10 to the negative 4. When we write out our ionization or equilibrium equation for nicotinic acid, we get nicotinic acid yields H plus and then our nicotinic acid ion. We write our equilibrium expression, so the concentration of the products over the concentration of your acid, nicotinic acid. Since we're in a 1-to-1 ratio, the concentration of H plus is going to be equal to the concentration of your nicotinic ion. Therefore, our Ka is just going to be that concentration of H plus squared over your initial concentration of the acid. So you get a Ka to be 1.4 times 10 to the power of negative 5. And that's all for this lesson. Have a great day, and I'll see you next time.
Okay, Helen, and here you have the quiz that is associated with this lesson. And also weak acids and basics problems.
Hello everyone, and welcome to Unit 1, Lesson 7. We're going to be talking about acid-base titrations today. The success criteria for this lesson. Students will solve problems related to acid-base equilibrium. Students will use appropriate terminology related to chemical systems and equilibrium, endpoint, equivalence point, and titrant. And success criteria, you'll do this by using acid-base titration data and the pH and equivalence point. Also listed here are your curriculum expectations. So in your previous chemistry course, you were a little bit familiarized with acid-base titration. So with titration, it's a chemical analysis involving the progressive addition of a solution of a known solute concentration called the titrant into a solution of unknown concentration called the sample. And the purpose of the titration is to determine the amount of a specified chemical in the sample, from which the molar mass and the concentration of the chemical may be determined. And this is possible because the titrant and the sample contain substances that react according to known stoichiometry. So in general, you have a sample which is placed in a receiving flask, and the titrant is dispensed from a sort of a long piece of glassware called a burette. So here's a closer look at your titration equipment. You have the concentration of an acid or base solution of unknown concentration, and we determine that concentration by the delivery from a burette of a measured volume of a solution of known concentration called the titrant. And if the sample in the flask is an acid, then the titrant used is a base and vice versa. So here we have our pipette. You have your stand holding everything up, attached to your burette, which has your base solution in here. And then in your Erlenmeyer flask or volumetric flask there, you have your acid in it. It's sitting on a white piece of paper, and you also have a measuring cylinder. There are also two reasons to run a titrant: to determine the concentration of an unknown reactant, or to determine the equilibrium constant for the reaction. And our pH is equal to our pKa at half of the equivalence point. And this is what we call the buffer region. We talked a little bit about this in the last lesson, but there's certain indicators that we use in a titration called the acid-base indicator. And they are weak acids which undergo a color change at a known pH. And they have a different color than their conjugate base forms. So this example of an acid-base indicator is phenolphthalein. So it is no color, it's colorless at a pH 2, 4, 5, and 7, but as soon as you reach a pH of 9, it will turn light pink. pH of 10, it will turn dark pink. There's a couple different indicators we can use, but you always want to select the indicator that undergoes a color change closest to the pH of the equivalence point. And we'll talk in a minute about what that equivalence point is. So some other two common acid-base indicators used in titrations is bromethyl blue and then methyl red, as well as phenolphthalein. Let's review some important titration terms. One being the analyte. And this is the analyte. This is the solution of unknown concentration but known volume. The titrant is the solution of known concentration. So your analyte plus your titrant gives you your products. Your equivalence point. The equivalence point in the titration is the measured quantity of titrant recorded at the point at which chemically equivalent amounts have reacted. In other words, the addition, you continue adding more of, or your acid-base titration, right, involves the reaction between the acid and the base. So you have a measured volume of your standardized titrant, and you add that to a known volume of your sample, and you continue adding more until the amount of reactant in the sample is just consumed by the reactant in the titrant. So you just have consumed all of your reactants, and at that point, it is the equivalence point, also called the stoichiometric point. So you also have your endpoint, and the endpoint in a titration is the point at which a sharp change in a measurable and characteristic property occurs. In this case, it is the color change in our acid-base indicator, and that indicator is either phenolphthalein, bromethyl blue, or methyl red. It's that substance that changes color when an excess of titrant has been added. Of the pH versus the volume added during the titration forms what we call a titration curve. So in this example, when the pH of the solution in the receiving flask is plotted against the volume of NaOH, that 0.1 NaOH solution, the result is this titration curve. The curve for the titration of the 0.1 moles per liter of HCl is typical for that. It's typical of that for the titration of any strong acid with any strong base, right? So this curve depicts the titration of the strong acid with the strong base. The curve sweeps up and to the right as NaOH is added, beginning at a pH below 7 and ending at a pH above 7. So that equivalence point in this case is reached at 7. And our indicator, for example, if we use phenolphthalein, it will change color between a pH of 8 and 10. But if we choose methyl red, we'll get that color change at a pH of 5 to 6. And here's the 4 different types of typical titration curves. The top left being a typical titration curve when you have a strong acid and a strong base. And then the top right, a strong acid and a weak base. The bottom left is the titration curve of a weak acid and a weak base. And then the bottom right is a weak acid with a strong base. This is a summary of the titration characteristics. So the type of titration, a strong acid and a weak base will have a pH at an equivalence point less than 7. A strong base and a strong acid will be approximately at equivalence point of 7. And then a strong base and a weak acid, it will be greater than 7. So again, taking a look at our titration curve and the characteristics of a titration with a strong acid and a strong base. For example, HCl plus NaOH yields NaCl plus H2O. This curve is typical of a titration with a strong acid and a strong base, so the curve sweeps up and to the right as you add more of your NaOH. And the equivalence point is reached at approximately a pH of 7. Strong acids and bases dissociate completely. And that is our typical curve and characteristics. Contrast, let's look at a weak acid with a strong base. So for example, NH3 plus HCl yields H2O plus NH4Cl. The NH4Cl dissociates into NH3 and H3O plus. So NH4 plus acts as your weak acid, creating an acidic solution at the equivalence point, so lower than 7. Your equivalence point pH is lower than 7, as you can see on the graph. And here we have an acid-base indicator table. So different indicators have different acid strength, and the acidity or pH of the solution at which an indicator changes color will vary. So these pH values have been measured and are reported in this table right here. So you can see the common name of the indicator and the approximate pH range that it changes. And note that in an acid-base titration, you get that pH change sharply near that equivalence point. So when selecting an indicator for a particular acid-base titration, the pH at the equivalence point must be known. So you want to see the color change at the correct point, so you know you've reached the end of your titration. And that looks like that's it. That's all for this lesson. Have a great day, and I'll see you next time. Hello everyone, and welcome to Unit 1, Lesson 8. This lesson is on buffers, so let's get started. Hello everyone, and welcome to Unit 1, Lesson 8. This lesson is on buffers, so let's get started. So all pH curves involving our titration curves, involving a weak acid or a weak base, have at least one region where a buffering action occurs. The buffering region is where the pH changes very little, despite the addition of a considerable amount of acid or base. So it's a region where you're adding more acid or more base at quite a high level, but the pH is changing very little. So it's like buffering. And the curves in these relatively constant pH regions are almost nearly horizontal. So that middle region of those titration pH curves. At a volume of titrant that is basically 1/2 the volume at the equivalence point. So you're adding more and more of the acid or base, but the pH is not changing. And the solution near these points has a special significance, which is called that buffer solution, or simply just a buffer. So it's a mixture of conjugate acid-base pair that maintains a nearly constant pH when diluted or when strong acid or base is added. And it's an equal mixture of a weak acid and its conjugate base. So they resist change in pH when a moderate amount of acid or base is added. A weak acid and a salt of its conjugate base will be a buffer, or you can have this weak base and then a salt of its conjugate acid together. Some examples of the pairs which make up buffer solutions are shown here in the table. You can have acetic acid with sodium acetate, phosphoric acid with potassium phosphate, oxalic acid with lithium oxalate, and carbonic acid with sodium carbonate. And we'll go through an example. So taking a look at this example, the titration of acetic acid with sodium hydroxide, the pH is approximately 4.7 at a volume of 12.5 milliliters of sodium hydroxide. Since 1/2 of the equivalence volume has been added, 1/2 of the original acetic acid has reacted. Right, so when a volume of titrant that is close to 1/2 the volume at the equivalence point is added in the titration when you have a weak acid and a strong base, the pH of the sample solution changes very little despite the addition of more base here. And this solution is called a buffer. So that highlighted plateau near the halfway mark to the equivalence point shows the buffering region of the titration. So buffering action can be explained using Bronsted-Lowry equations. So when a small amount of sodium acetate is added to the acetic acid acetate ion buffer, this following reaction occurs. So the small amount of OH minus ions added would convert a small amount of acetic acid to acetate ions. So the overall effect is a small decrease in the ratio of acetic acid to acetate ions in the buffer, and a slight increase in the pH. So this small change and the consumption of some of that added hydroxide ions in the process explains why the pH is small. And this buffer would work equally well if a small amount of a strong acid were added instead. Right, so the hydrogen ions are consumed, and the mixture now has a slightly higher ratio of acetic acid to acetate ions, and a slightly lower pH than it would have had if there was no buffer present. So there is a limit to the amount of strong acid or base that a buffer can neutralize before its pH begins to rise rapidly. So they have capacity. A buffer's capacity is determined by the concentrations of its conjugate acid-base pair. And the amount of acid or base that can be added before considerable change occurs in the pH can be calculated, and that's considered to be the capacity of that buffer. So we can go through some sample problems. So for example, calculate the change in pH that occurs when 0.1 moles of HCl is added to 1 liter of an ammonium chloride buffer containing 0.3 moles per liter ammonia and 0.33 moles per liter ammonium, or the NH4 plus at equilibrium, and assume no change in the volume of the buffer. So we write out our knowns. 0.1 moles of HCl is added. We have our concentration of NH3 to be 0.33 and our concentration of NH4 plus to be 0.33. We write out our equilibrium equation, NH3 plus H2O yields NH4 plus OH minus. We write out our Kb, our constant expression, which is the concentration of each of those products over the concentration of that strong base, the NH3. And we find our Ka from Appendix 9 or from your table. The Ka of NH4 plus is 5.6 times 10 to the power of negative 10. We can write our relationship between Ka and Kb is equal to Kw. So to solve for Kb, we rearrange that relationship to Kw over Ka. We know our Kw is always 1.0 times 10 to the negative 14. And we just found our Ka from the appendix or from our table, or it's given. We find our Kb to be 1.8 times 10 to the negative 5. Now to get our concentration of OH minus, that is Kb times the concentration of NH3 over the concentration of NH4 plus. Those cancel each other out. And we get the concentration of OH to also be 1.8 times 10 to the negative 5. Then we can use our POH logarithmic formula to determine the POH. When you subtract that from 14, you get our pH to be 9.26. However, we're not quite done there yet. Since HCl is a strong acid, it ionizes completely to H plus and Cl minus. Therefore, the concentration of H plus added is our moles, 0.10 moles over 1 liter. So that's 0.1 moles per liter. And then the added H plus is neutralized in a 1-to-1 reaction as shown by that following equation there. Right, it's 1-to-1. So our concentration of NH3, our final concentration is 0.23 moles per liter. And our final concentration of NH4 plus is 0.43 moles per liter. We can write out our Kb again for that, which is for this reaction, which is your NH4 plus times your concentration of OH minus over your concentration of NH3. Rearrange that for the concentration of OH and solve that. Our POH, therefore we use our log equation again, we get our POH of 5.02. Subtract that from 14, and we get our pH to be 8.98. So the pH of the ammonium chloride buffer decreased from 9.26, our initial pH, and then our buffer pH to 8.98. Moving on to buffers in action. So the ability of buffers to maintain a relatively constant pH is important in many biological processes because certain chemical reactions need a specific pH. So many aspects of our cell functioning and metabolism are very sensitive to pH changes. So we use buffers to keep a small pH range in our bodies. So for example, each enzyme carries out its function optimally over a small pH range. And one really important buffer within living cells is the conjugate acid base pair of H2PO4 minus and HPO4 2 minus. Another one is the conjugate acid base pair of H2CO3 and HCO3. And our blood plasma also has a remarkable buffering capacity. So head and different parts of our body maintain the same or small pH levels. Always buffers to stay at that pH range for optimal functioning in our bodies. Human blood plasma normally has a pH of about 7.4, and any change in pH of more than 0.2 For example, induced by poisoning or disease is life-threatening. So if the blood were not buffered, the acids that we would absorb from simply drinking a glass of orange juice would probably be fatal. That is just reiterating what I had just said. The buffering fraction of NaCl solution and of your blood plasma. So neutral saline has an initial pH mixture of 7.4, but the final pH after adding 1 milliliters of some acid, it goes all the way down to 2. In contrast, our blood plasma, initial pH of 7.4, and when you still add a bunch of acid, it stays by 7.2, and that's because of the buffers. So some more buffer systems in our bodies. So buffer systems can be in our intracellular fluid or in our extracellular fluid. In our intracellular fluid, we have a phosphate buffer system and a protein buffer system. The phosphate buffer system has an important role in buffering the pH of like our urine, for example. Protein buffer systems contribute to the regulation of pH in our intracellular and extracellular fluid. So for example, our hemoglobin buffer, amino acid buffer, and then plasma protein buffers. And then in our extracellular fluid, we have a carbonic acid bicarbonate buffer system, which is the most important one for our extracellular fluid. So buffers in our blood, we talked a little bit about. The pH of blood is 7.35 to 7.45. So changes in pH below 6.8 and above 8 may result in death. So the major buffer system in our body fluid is the carbonic acid carbonate, H2CO3 and HCO3 minus buffer system. And for example, some CO2, some carbon dioxide, which we know is a waste product in cellular metabolism, is carried to our lungs for elimination, but the rest of it dissolves in our bodily fluids, which forms carbonic acid, which dissociates to produce bicarbonate and hydronium ions. So again, it's contributing to that buffer system. Here's the equations showing it there. Buffers are also super important for many consumer, commercial, and industrial products as well. So fermentation, the manufacturing of antibiotics requires buffers to optimize yield and to avoid side effects. Production of cheese, yogurt, and sour cream is dependent on buffers to control pH. Right, since an optimum pH is needed to manage the growth of bacteria or microorganisms in those products and allow enzymes to catalyze the fermentation process efficiently. Sodium nitrate and vinegar are widely used to preserve food, and part of their function is to prevent the fermentation that takes place only at certain pH levels. These next couple slides is the same example that we went through previously. So if you want to review that, you can go through these next slides. It's just the same example, but the solutions are a little bit bigger to see. Again, here's part 2 and 3 of that same example. And here's the final half of the solution for the that same question we went through in the beginning of the lesson, the pH of the ammonia chloride buffer. And that is the end of this lesson. Have a great day, and I'll see you next time.
Buffer solutions resist changes in pH. And so let's think about a solution of a weak acid and its conjugate base. So here we have HA, which is our generic weak acid, and so the conjugate base would be A minus. And a buffer solution needs to have substantial amounts of both present, and that's what I'm trying to represent over here. So we have a beaker, right, that has, in this case, equal amounts of HA and A minus. And to our buffer solution, we're going to add some strong acid, so a source of protons. So I'm going to draw a proton in here, so H plus. I could have written H3O plus because H plus and H2O give you H3O plus. I'm just writing H plus to make it a little bit easier to think about. So if you're increasing the concentration of H plus ions, or you're increasing the concentration of hydronium ions in solution, you would think that would decrease the pH dramatically. And that would happen if you didn't have something to react with the protons in solution. But we do in our buffer solution, right? We have A minus, we have our base. The base is going to pick up this proton, and H plus and A minus are going to form HA. So we're going to make more of our weak acid here. So let's see, we started out with some weak acids. Let me go ahead and draw that in here. So some HA. And then we're going to make more because H plus and A minus give us HA. So we're making more of our weak acid here. What about A minus? All right, well, we're going to use one of these up to make HA, right? So now we have only two of these left. So we're decreasing the concentration of A minus. But what we've done is we've effectively removed protons from solution, and that's how a buffer is able to resist a change in pH if you add acid. What about if you add base? So next, let's think about our buffer solution. And this time we're going to add a strong base. So we're going to increase the concentration of hydroxide ions in solution. So if we increase the concentration of hydroxide ions in solution, you would think that would increase the pH, right? And it would, except for the fact that we have an acid that can react with our base, right? So we have some weak acid present here, and the hydroxide ion is going to pick up a proton from HA, right? So we have H plus here. So OH minus and H plus give us H2O. So we're going to make water here. Right, so we're going to lose some of our weak acid. So we started with 3, and now we have only 2 left here. And if OH minus, if hydroxide takes a proton away from HA, then we're left with A minus. So we're going to increase the amount of A minus that we have, right, in solution. So let me go ahead and draw that in here. So once again, we've effectively buffered against a change in pH because the hydroxide ions that we added, right, were reacted with the acid that was present. So we've effectively removed hydroxide ions from solution. All right, so that's the idea of a buffer solution. Let's see if we can derive an equation that will allow us to do some calculations. And so next, let's look at what we have down here, right? So we know that we have in a buffer, we have substantial amounts of HA and A minus present. And so we have this reaction at equilibrium. So for our equilibrium expression, right, concentration of products over concentration of reactants. So here we have our concentration of products over our concentration of reactants, once again leaving water out. Let's take the negative log of both sides of this. So we're going to take the negative log of Ka, so that would be negative log of Ka here, and the negative log of all of this, which would be equal to the negative log of all of that. And I'm going to write it a little bit differently. I'm going to put the concentration of hydronium ions out front here, and then have concentration of A minus over concentration of HA. All right, I wrote it like this because it makes it a little bit easier to see a property of a logarithm. Let me just go ahead and write down the property that I'm referring to. If you have log of A times B, that's the same thing as log of A plus log of B. And here we have the negative log. So the negative log of AB is equal to the negative log of A plus the negative log of B. So I'm just going to write minus the log of B here. And in this case, right, concentration of H3O plus, that would be A. Right, so this would be A, and then this over here would be B. Right, so let's think about what that would give us now. So let's get some more space and let's think about our log property. So on the left side, we have negative log of Ka. And the right side, we would have negative log of A. So that would be negative log of concentration of H3O plus, right, minus the log of B here. So that would be minus the log, and B was this right here, minus the log of A minus over HA. All right, so we can keep going here because we know the negative log of Ka, right, the negative log of Ka is equal to the pKa. So this is equal to the pKa. And then over here, we have the negative log of the concentration of hydronium ions. That's equal to the pH, right? So negative log of concentration of H3O plus is equal to the pH. And then we have minus log of the concentration of A minus over the concentration of HA. And so we can rewrite this in for our final equation. So we're just going to rewrite this, solve for pH. pH is equal to pKa plus the log of A minus over the concentration of HA here. This is called the Henderson-Hasselbalch equation. So right here is the Henderson-Hasselbalch equation. It's very useful when you're doing buffer calculations. Right? We'll look at examples of this in the next video.
Okay, Hella, are you there?
Yes.
Okay. So this was basically like a review because you guys you're supposed to review all of this on your breaks, basically. And so I just went over it with you again. And yeah, so be sure to work on this lesson here and also the multiple choice quiz.
Yes, of course.
And you said that you did start on the test?
Yes.
Okay. So this is the test. You can print it out. Can you print it out, work on it, and then submit the answers?
Sure.
Usually
I've
do.
started on a separate piece of paper, but if you'd like, I'll print it out.
Yeah, print it out. And then write on it, practice on it. Also just do your equations on it, and then just, yeah, I think that'll be easier if you just print it out. All the information will be in front of you. And then you can refer back to the lessons, right? That we did. Did you say you're
Yeah.
see the lessons or no?
I can't see the first
Can
two
I see
lessons.
can you share your page with me?
Yes, of course.
Or share your screen? There should be the bar, where it says mute, start video, security.
Yeah.
So right